concepts are new. In the 37th lecture, we speak more about correlation functions. Well, we introduced the concept of correlation function as the expected value of the product of two random variables, x1 and x2. They could belong to the same process. If they belong to the same process, then we say it is autocorrelation. If they belong to different processes, for which sometimes we shall use a different symbol, x1, y2, we shall reserve this symbol for autocorrelation. That is, we mean that the two random variables x1 and x2 come from the same process. If they come from different processes, then we shall call this as the cross correlation. Autocorrelation function and cross correlation function. As you shall see later, cross correlation function depends on which way we take it. It could be either x1 or x2, or it could be x2 and y1. They are not necessarily equal, as you shall see later. Now, if the processes are stationary, then well, before stationarity, obviously to be able to calculate the expected value or the expectation, we require the joint probability density function, that is P of x1 and x2, or P of x1 and y2, or x2 and y1. Joint probability density function is a requirement. Now, in a stationary process, such statistical measures like probability density function, they are independent of the origin of time. They only depend on the difference between the two time intervals, and in that case the autocorrelation function, for example, does not depend on exactly where the two variables, exactly at what points of time the two variables are considered. They only depend on the time difference between the two. And we showed last time that Rx tau, if it depends on the time difference only, then Rx tau must also be equal to Rx of minus tau. That is, the autocorrelation function is an even function. It also followed from last time's discussion that Rx of 0, which is the expected value of xt multiplied by xt, obviously is x squared bar. Alright. These are some of the two properties that we had already discussed. And then we also introduced a quantity called time autocorrelation function, Rx of tau, which is defined as the time average of xt and xt plus tau, which means that you take the integral of xt plus tau dt over, let's say, minus t to plus t, some interval minus t to plus t, divide by 2t, then it will be the time average of the product, and then allow capital T to go to infinity. This is the definition of Rx of tau. And for for ergodic processes, the time averages are the same as ensemble averages, and therefore Rx of tau is equal to time autocorrelation function for ergodic process. An ergodic random process is defined as one in which the time averages are the same as the ensemble averages. Well, strictly this is a consequence of the definition. The definition is that an ergodic process is a stationary random process in which every member of the family has the same statistical characteristics as that of the ensemble. And it is a consequence of that definition that the time averages are the same as ensemble averages. Last time we wanted to find a physical meaning of the ensemble average, Rx tau, or the autocorrelation function, and to that end we had defined a random process or a random time function as x of t minus rho x of t plus tau. And we showed the meaning, and we showed the physical interpretation of rho is that the minimum rho, the value of rho, the value of rho required to minimize the mean squared value of yt, which is the difference between the two random variables x1 and x2, with x2 weighted by rho, y squared bar is minimized when rho becomes equal to, when rho is equal to Rx tau divided by sigma x squared, and therefore we had called rho as the correlation coefficient. Sometimes it is called normalized correlation coefficient, because obviously there is a normalization with respect to the variance of x. It was the variance provided. Yes, Pankaj.
Sir, why are we taking xt minus rho times xt plus tau? To find the difference in two signals, we must be only considering xt minus xt plus tau. So why are we considering rho?
Why are we considering rho? Rho is a measure of how similar the two waveforms are. If they are exactly similar, then rho is plus 1. Alright? In other words, y squared bar, minimum value of that will be 0. And therefore, we intend to keep a coefficient which will be a measure of the similarity. And we show that rho is proportional to Rx of tau. For example, the value, the limits of rho are minus 1 and plus 1. Rho equal to plus 1 will exactly mean what we want, what you want, xt minus xt plus tau. And under that condition, y squared bar minimum value, well, not minimum, even y squared bar minimum, if we take rho equal to 1, rho is fixed, so there is no minimization problem. Y squared bar is equal to 0. Alright, so in order to cater to other possibilities of values of rho, that is, the two waveforms xt and xt plus tau could be completely dissimilar, then the value of rho is 0. Alright, they could be similar, but with a change of phase. For example, xt and minus xt plus tau could be similar, then rho is minus 1. So this is why we had introduced this term rho, and rho, instead of characterizing in terms of autocorrelation function, it is more convenient to characterize in terms of rho. Alright, and rho rather than Rx tau is taken as a measure of similarity or dissimilarity between the two random processes. Alright, so rho can vary between minus 1 and plus 1. To make these ideas a little more explicit, we consider now an example, and I want you to follow this example very carefully. I shall go very slowly. The example is that of a random process which is depicted here. I shall explain the random process. The random process is discrete valued, that is, the let me take the variable xt can take either of two values, either plus x0 or minus x0. Alright, it can take either plus x0 or minus x0, nothing in between. So it's a binary valued random variable. There are two possible levels, and therefore this is a discrete random process. The time is not discretized, time is continuous. T, it is, xt is a random function, and it is a member of an ensemble. It is a member of an ensemble. It is only one of them is shown here, only one from the family, xt. The property is that there is a reference point t0 from which the waveform starts. Now t0 itself is a random variable. T0 itself is a random variable which can take on values randomly between 0 and Ta, some quantity Ta. In other words, T0 is a random variable having a range of Ta from 0 to Ta, T subscript A, with a uniform probability density. In other words, is the point clear? The starting point or the reference point of the waveform goes to the right and also to the left. But there is a reference. This reference is not the origin. it can go to the origin. T0 can be 0, but T0 varies between 0 and some quantity small t subscript small a. So T0 is a random variable and it is uniformly distributed over this range, which means that any value of T0 between 0 and Ta is equally probable. It is uniformly distributed, alright, which means that if I plot P of T0, small p of T0, that is the probability density of the random variable T0, then it is uniform over a certain range 0 to Ta, alright. Can you tell me what this value shall be? 1 by Ta. So this is the situation with regard to T0. T0 is a random variable which is characterized by this, alright. The next point about this particular random process is that once the reference is fixed in one member of the family, every Ta seconds later or earlier, the waveform, the value xt, has two options. It can either change or remain the same. If it changes, for example here, the value was x0. At the reference point, it changes to minus x0. Now, at Ta seconds later, which is here, T0 plus Ta, the value can either remain the same, as I have shown in this thick graph, or it can change to plus x0, as I have shown by the dotted lines. Alright? This is the freedom. And therefore, xt, the value of xt in any interval, let's say T0 to T0 plus Ta, is constant at either plus x0 or minus x0. It has two possibilities, alright, with equal probability, that is, the probability that in the interval T0 to T0 plus Ta, the value of the random variable is plus x0 is equal to the probability that the value is minus x0, and the probability of each is half, with equal probability. Is the point clear? So, in one member of the family, a typical member of the family, at T0 plus Ta, it has not changed. It remains the same. At T0 plus 2 Ta, now the constraint is that it is mandatory that every Ta seconds later, there is a freedom of change. The freedom may be exercised, may not be exercised. And it is in this sense that small xt is a random variable. Not only its origin or reference is random variable, but the value is also a random variable. Only choice is plus x0 or minus x0. Now you see at T0 plus 2Ta also, I have shown that it does not exercise its freedom. It remains at minus x0. For another member of the family, maybe it changes. For another member of the family, T0 is not necessarily here. It could be somewhere here or it could be here. Alright? But not exceeding Ta. It remains between 0 and Ta. Why this constraint, I will explain in a moment. Let's understand the problem clearly. If you understand a problem in random variables or autocorrelation and things like that, if you understand a problem clearly, half of it is solved. Alright? It is always true. So let's understand the problem clearly. At T0 plus 3Ta, I have shown that the function, this member of the family, exercises the freedom for going from minus x0 to plus x0. Then it remains at plus x0 over this interval, that is T0 plus 3Ta to T0 plus 4Ta, and then again at T0 plus 4Ta, it exercises its freedom of going to minus x0. But at T0 plus 5Ta, it remains the same. Alright, for other members of the family, the picture can be completely different.
So here, when it's at plus x0, it can stay at plus x0 for infinite, for any amount of time, or it has to come down?
No, it can remain so for the rest of the time. But every Ta seconds, there is a freedom. It may exercise the freedom, it may not exercise.
And in this case, you haven't shown it, but at T0 plus 2A, even at that point, it had a freedom to go up.
That is correct. It had a freedom to go up, but it has remained the same. Alright? Okay. So, you can draw other members of the family. where T0 is not necessarily this point, T0 is distributed. Now you can ask me, why is T0 restricted between 0 and TA? Well, if T0 is not restricted between 0 and TA, you don't restrict it. You go over 0 to 2 TA or 0 to 5 TA, whatever it is, alright. The picture will be the same, because every TA seconds, there is a kind of a periodicity, but random periodicity. It may or may not change. Every TA seconds there is a possibility of a change. So this is a sufficient description. As far as the ensemble is concerned, it will appear that the value, that the change from minus x0 to plus x0 can occur at any instant of time. Isn't it right? Because T0 itself is a random variable. It suffices to concentrate on T0, random variable between 0 and TA. It suffices. You don't have to consider any other value. The question now is, this is a process. I can draw a number of such members of the family. What we have to do now is to find out the autocorrelation function as a function of tau. That is, I have shown a typical T1, two instants of time. One is T1 and the other is T2. T2 is T1 plus tau. I have shown a typical instance of two random variables from the same process. Now, if you go over the ensemble, if you go over the family, the value may be minus x0 or plus x0. Now, there is one more constraint, that, notice this carefully, this is one of the key constraints, that is, the value of the random variable within one interval is completely independent of the value of the random variable within another interval. Alright, which means that x1 and x2 are statistically independent if they lie in different intervals. If they lie in the same interval, for example, tau is so small that x1 and x2 are both within this interval, then obviously the product x1 and x2, product of x1 and x2 is simply capital X0 squared. Isn't that right? So they are perfectly correlated. Okay? On the other hand, if they lie in different intervals, for example, one interval is here and the other is here. One time instant is in this interval, the other is the next one, or maybe the next one, then they are completely independent of each other. Which means that expected value of x1, x2 is equal to expected value of x1 multiplied by expected value of x2. This is what is meant by statistical independence. Alright. We also assume, condition of the problem, that it is a zero mean process, that is x bar is equal to 0. Alright. Then under this condition, if x bar is equal to 0, then what is the autocorrelation function? What is the autocorrelation function if T1 and T2 lie in two different intervals? What is the autocorrelation function? Obviously, yes?
Can't say.
You can't say?
Depends upon the ensemble characteristics. We only know that they are independent. They can be.
They are independent. So, alright. So, E of x2, x1, x2 would be equal to E of x1 multiplied by E of x2, which is equal to x1 bar times x2 bar. That's zero mean processes. And therefore, the product is 0. Alright. Which happens, let me go back, which happens if, which definitely happens if T1, if tau is greater than TA. If tau is greater than TA, obviously T1 and T2 must be in two different intervals. Alright. And therefore, if tau is greater than TA, Rx tau is equal to 0. Is that clear? Definitely, there is no question. Tau is greater than TA, Rx tau must be equal to 0 because x1 and x2 are statistically independent of each other. On the other hand, if tau is less than TA, we have to consider two cases. Tau is positive and tau is negative. Let's first consider tau as a positive quantity. Tau lies between 0 and Ta. Notice this figure carefully. Is it sufficiently clear on the monitor? Okay. No? Should I draw it again? Okay, there is no harm in making it more clear. Alright, this is T0, then this is T1, this is T0 plus Ta, then T0 plus 2 Ta, and let's say this is T1 plus tau. What we are considering is tau greater than 0, tau greater than 0 but less than Ta. If tau is greater than Ta, then we have established that Rx tau is equal to 0. If tau is less than Ta, and it's a positive quantity, obviously two situations can arise depending on where T0 is. Suppose your T1 and T1 plus tau, this amount is tau and this amount is tau A. Obviously tau is less than tau A, but T0 can be such, T0 is a random variable, T0 can be such that T1 and T1 plus tau lie in two different intervals. Alright? And therefore again the expected value shall be equal to 0. So our only concern therefore is when T1 and T1 plus tau are in the same interval. Well, that can happen if tau is less than Ta, provided T0 is suitably located. For example, here this is T1 and this is T1 plus tau. Suppose T0 is here. T0 is here. This is T1. This is T1 plus tau. Then T0 plus Ta is somewhere here. Alright. Then T1 and T1 plus tau are in the same interval. Alright. And it is only under this condition that the expected value of the product shall be non-zero. Alright. So what we have to find out basically is the probability that T1 and T1 plus tau are in the same interval. To find out the values of Rx, to find out the values of tau for which Rx of tau is non-zero, what we have to do is to find the probability that T1 and T1 plus tau are in the same interval. Let me write it down.
Sir, just a second, sir. So here, what exactly do we mean by T0? I mean, what is T0? Is it that
T0 is a reference. It's some reference.
It's different for every function in ensemble.
That's right. It's a random variable. It may be by chance the same for two of them, but it's a random variable.
Yeah. Sir, the point is that you said that T1, in this case, T1 and T1 plus T1 plus tau are fixed. So
No, they are not fixed.
I mean,
We are trying to find out the value of Rx as a function of tau. So we are taking different kinds of tau. First we take tau greater than Ta. Now we are taking tau positive but less than Ta. And we are saying that T0 can be such that T1 and T1 plus tau are in two different intervals.
Sir, but those are two different experiments. I mean,
Correct.
What I want to ask is that in this case you moved T0 such that T1 and T1 plus tau
Are
lie
in the same interval. Yeah.
But couldn't we have moved T1 and T1 plus T tau together so that they lie in the same interval? And what is the problem with that?
What is the problem? No, there is no problem. The only problem is it's a stationary process and therefore it doesn't matter where we take T1. Isn't that right? The Rx tau shall be the same. What I am asking now is, all that you have to find now is the probability that T1 and T1 plus tau are in the same interval. Now, isn't this probability directly proportional? Now I am making a statement. I will verify it a little later. Isn't this probability directly proportional to the difference between tau and Ta? Suppose tau is greater than Ta, then it's 0. If tau is less than Ta, then it is non-zero. But suppose tau tends to 0, then obviously the probability is 1. And therefore, from this qualitative argument,
Why is it 1, sir? So they may lie on different sides and it may still tend to 0.
If tau is 0, then T1 and T1 plus tau are the same point.
Yes, sir.
And at the same point, they must be in the same interval.
So but suppose it lies on T0 plus TA, then it will be undeterministic in which interval it's lying.
T0 plus TA, it's either plus x0 or minus x0. There is no value in between. There is no value in between. Okay?
Transition point.
Transition point will take either the upper one or the lower one. It doesn't matter because the product is still x0 squared. Whether it is plus x0 or minus x0, it doesn't matter. Alright? That's the beauty of the problem. So the probability that T1 and T1 plus tau are in the same interval, I said it's proportional to TA minus tau. Okay? What is the proportionality constant? Obviously it is the probability density of T0. Isn't it right? And what is the probability density? 1 by TA. Doesn't this fit exactly? That when tau equal to 0, the probability is 1. When tau is greater than TA or tau equal to TA, the probability is 0. Tau greater than TA, obviously, from physical considerations, it is 0. So this is the probability.
So if we have taken some other function also which can satisfy, it could have been this square or cube or anything.
It could it could have been the square.
This particular function.
Yeah. Okay.
And how do you know like that it was originally proportional to TA minus tau?
How do you know it was originally proportional? You see, the probability density of T0, P of T0 is 1 by T, it's uniformly distributed. And T0 is a random variable. The probability, yeah, you have a point.
Then how does T0 come into picture? We are only talking of T1 and tau with respect to TA.
Tau becomes greater than TA, then it becomes negative. So
Okay. No, this formula is not true for tau greater than TA.
Writing it for tau less than t.
It is true for tau less than TA. 0 less than tau less than TA. It is true only for this range. Tau greater than TA we have already seen from physical considerations is equal to 0. Alright. Now, the question whether it is a square or not, well, that is a tricky question.
Sir, we can easily calculate it, sir. You have to taking the number line, what we have taken the number line, and see what is the reason TA should lie, so that they will be in the same interval. And this is the interval for TA, so that they will be in different interval.
Yeah,
Then we will
that's,
take
that has been taken care of. That's why we said that is proportional to the difference.
So
But
it will
what
come
is
out to
asking is why isn't it proportional to the square?
Sir, because that is uniformly distributed.
Because that is uniformly distributed. That is the answer to the question. It is uniformly distributed, and therefore, then otherwise, if it was proportional to the square, then it would have been a non-linear function. It would not have been a
So
constant.
how does T0 come into picture, sir?
It is T0 which makes them either in the same interval or in different intervals. And therefore, pardon me?
it is TA.
No. The location of T0. T0 is uniformly distributed over TA. And therefore, probability density of T0 is 1 by TA. But it is the location of T0 with reference to T1 which determines whether the two values are in the same interval or in different
So
intervals.
this means T1 and T1 plus tau are fixed and we are just moving T0 such that
We are not moving. We are simply observing over the ensemble.
Yeah.
For some, there is a probability that T0 is such that T1 and T1 plus tau are fixed over the ensemble now, because x1 and x2 are fixed. We are only looking at different families, and we are asking what is the probability that T1 and T1 plus tau are in the same interval. Alright. And this probability is proportional to the difference between the two, and the proportionality constant is P, small p of T0. If we know the probability, then of course we know Rx tau also, don't we? What is Rx tau then? Oh, before that, suppose tau is negative. Suppose tau is negative instead of positive. Then what would be the modification in this formula? It will only be TA plus tau in that case. So it would be TA minus mod tau. and in this case we are not assuming that tau lies between 0 and Ta. All we are assuming is mod tau less than Ta. After this modification, you can immediately write down the expression for Rx tau. Rx tau, if T1 and T1 plus tau are in the same interval, then what is the product of x1 and x2? Obviously x0 squared. That has to be multiplied by the probability that T1 and T1 plus tau are in the same interval, and therefore it would be simply 1 minus tau divided by Ta. Alright, this is the final result for autocorrelation function. And if you plot this, if you
Can you
plot
explain how you get this once Rx tau?
Rx tau, okay. The value of x1, x2 multiplied by the probability that x1 and x2 are in the same interval. Alright, so x0 squared multiplied by this probability. And if I plot it now, Rx tau, you see that it would be a triangular function like this, where this is Ta and this is minus Ta, and this is tau, which also physically is a linear function. You can see this x0 squared 1 minus tau by Ta. Physically what it means is that the smaller tau is, the larger will be the autocorrelation function. That is, the smaller tau is, the more similar will be xt and xt plus tau. In fact, when tau is 0, they are identical. Can you tell me what this value is?
x0 squared.
X0 squared, that is right. Okay, when tau is 0, they are absolutely identical. As tau increases, the probability of dissimilarity increases, and therefore Rx tau decreases. And when tau exceeds Ta, the autocorrelation function is absolutely 0. Alright, if you have understood this problem, you have understood a lot of the concepts of autocorrelation that we have discussed so far. Now some interesting properties of the autocorrelation function, properties of Rx tau. We have already derived that Rx of 0 is x squared bar. We have already derived that Rx of tau is equal to Rx of minus tau. That is, Rx of tau is an even function. The third property, which is quite remarkable, is that Rx of tau, you notice here, you notice in this example that Rx of tau is less than Rx of tau is less than Rx of 0. Can Rx of tau be negative?
Yes, sir.
Yes, it can be negative. Now, it is in general true. Can Rx of 0 be negative? No, because it is the mean squared value. Alright, so Rx of tau in general, here it is positive, but in general it can be negative. And in general, it is true that mod of Rx of tau is less than Rx of 0. In other words, the property is that Rx of tau is, mod Rx tau is a non-increasing function of tau. Alright, it can be constant.
Less than equal to.
Less than equal to. Well, I'm hesitating to do that because of a reason which will be clear later. Well, so this property is that Rx of mod Rx tau. Alright, let's put the equality sign. This is a remarkable property, and the proof is also remarkable. What we do is, to prove this, we follow the proof. This is the style of proof that one has to use in such problems. Expected value of x1 plus x2 whole square. Alright, that is a combination plus minus, combination of two random variables. You create a third random variable, which is either the sum or the difference between two random variables taken from the same process. Alright, then you see this would be e of x1 squared plus e of x2 squared plus minus twice e of x1 x2. Alright, now is it okay? So E of, and what can you say about this expected value? Expected value of x1 plus x2 whole square, that is x1, it must be positive, greater than equal to 0. Why? Because it's the mean squared value of the third random variable x3. Mean squared value cannot be negative, so it must be positive, which means that E of x1 squared, let me write it again, plus E of x2 squared must be greater than equal to minus plus twice, what is E of x1 x2? Isn't this simply Rx of tau? Agree? Okay. What is E of x1 squared? This is x squared bar, and this is also x squared bar, E of x2 squared, because the processes are stationary, and therefore the mean and averages shall be the same irrespective of the time origin. Therefore 2x bar squared is greater than equal to minus plus 2 Rx tau. Now what is x squared bar? Rx0, and therefore you can cancel this 2. Rx0 shall be greater than equal to minus plus Rx tau. Now if Rx tau is positive, the argument is now very simple. If Rx tau is positive, and if you retain the negative sign here, obviously it is automatically satisfied, because Rx of 0 can never be negative. Rx of 0 is positive, and if Rx of tau is positive, obviously it's greater than minus Rx tau. If Rx tau is positive and the sign is positive here, then obviously Rx of 0 is greater than Rx of tau. Alright? And therefore in general, Rx of 0 must be greater than equal to mod of Rx of tau. Is that clear? This is the third property, a very remarkable property. And
Sir, you are using that the process is stationary. Is it necessary to use that?
yes, because otherwise x1 squared bar may not be the same as x2
I
squared bar.
think the property holds even if the process is not stationary.
Then you have to use x1 squared bar plus x2 squared bar. If the process is not stationary, then you cannot equate these to Rx of 0. You have to use Rx of T1, T2 instead of Rx tau, because the averages will depend on the time origin. So the stationarity is implied in this derivation, and in practice, in most of the cases, it is only stationary processes that we shall be concerned with.
Question, sir.
Yes, please.
What are x1 and x2? I mean, here, what are they? I mean, are they members of the same ensemble? Or
No, they are random variables over the ensemble. It is time which is frozen, T1 and T1 plus tau.
random variables
Over the ensemble, yes.
They're dependent on t. I mean, T1 is something, x1 is something like x at T1.
X at T1,
Varying
that's
over
right.
all.
Over the ensemble. Well, this is an ensemble, so from one member to another, the values that it takes can be different. Alright? Yes.
When we say that Rx of 0 is greater than equal to minus plus of Rx of tau, this means that it is greater than both minus and plus.
That is correct. Because the process could be either x1 plus x2 or x1 minus x2. And Rx of tau could be either positive or negative. So in general, if this is satisfied, then this is satisfied. Alright? Okay. The next property is, this would be number 4, that if xt has a DC component. What does it mean? It means that x bar, if it is an ergodic process. No, DC component means in time. That means a random time function, its DC component is its average value. Only if it is ergodic, then it will mean that x bar is not equal to 0. Not otherwise. But if xt has a DC component, alright, then Rx tau also has a DC component. Will also have a DC component. The proof is quite simple. first take the trivial case that xt equal to x0, some constant, it's a DC. Alright, obviously what is Rx tau? Rx tau would be simply what? The probability is 1, isn't it? It's constant. So all members, it's a very trivial case. So it will simply be Rx tau equal to x0. So if xt is DC, then Rx tau is also DC. Now take the non-trivial case when xt is a DC component plus some component nt, let's say, nt, n of t, where obviously the average value or the DC value of n of t shall be equal to 0, alright, DC value equals to 0. It is only the time varying component and this is the DC value. Then obviously E of xt plus tau would be equal to E of x0 plus nt multiplied by x0 plus nt plus tau. Alright, and if you multiply this out, then you see that it would be x0 squared, x0 multiplied by x0, expected value shall be x0 squared, plus expected value of nt multiplied by x0. Now we assume that this is a zero mean process, that is n0, n bar equal to 0. We assume that it's a zero mean process. Then what will be the result? x0 nt plus tau and x0 nt expected value shall be 0. There shall be an expected value of nt multiplied by nt plus tau, which would be simply, because this is a zero mean process, we can write that as
R.
no
n of that.
n of what? Let me tell you. It is expected value of nt multiplied by nt plus tau.
So Rn of
tau. Alright? This is what we get. And therefore, the Rx tau has a DC component, x0 square. Alright? Has a DC component. Rn tau will vary with tau, but x0 squared shall remain constant. In a similar manner, if x of t,
So but
yeah,
then why in this case when we had Rx was E x1 x2, then why was it equal to 0? We had, you had shown us that E x1 x2 is equal to E x1 into E x2, which is equal to 0. So how was that equal to 0? That was x at t1.
E of xt plus tau, yes.
It shown that this is 0.
No, we didn't
No,
show that this is
you
0.
You showed now that E x1 x2 is equal to E x1 E x2, which is
Provided x1 and x2 are statistically independent of each other, not in general. Okay? Alright.
So one more question.
Yes.
Sir, how can we say that Rn of tau doesn't have any DC component? If it has a DC component minus x naught square.
No. You see, what are you interested in showing? We are interested in showing that if x of t has a DC component, then Rx of tau shall also have a DC component. This is what, and therefore we said x of t, the DC value is x0.
So suppose Rn of tau has a DC component minus x naught whole square.
So the question is, suppose a function, suppose
No, listen. If we have not yet proved, but it can be proved that if x of t, if n of t has a DC component, then there shall be a DC component in the autocorrelation function also.
but not the other way.
What? Yeah, the other way around is this. What is it that we have assumed here? Yeah, it is also true the other way around.
So, but
If
then
xt
we should
does
say if
not
and only
have-
if, sir.
Pardon me?
So in the statement, then we should say if and only if.
Correct.
If
The-
and only if it has a DC component, then
There are situations which are exceptions, and therefore I was hesitating. But it is true. Let's agree to this. That not agree. You can also show there are some exceptions which I don't want to enter into now. But let me clarify the sequence. Sequence is if xt has a DC component, then Rx tau has also a DC component. And to be able to demonstrate this, what we did was, we broke xt into its DC component plus its AC component nt. And AC component means that its DC value is equal to 0. Alright, and therefore ENT times NT plus tau is Rn tau, which cannot have a DC component.
So we haven't proved this.
We haven't proved that. All
That
right.
an AC component.
All
cannot
right,
have
I
a
leave that proof to you. It can be proved. The next property is that, what would be sixth? If xt has a periodic component, alright, if xt has a periodic component, then Rx tau also has a periodic component, The interesting part is the frequencies do not change with the same frequencies. With the same frequency or frequencies depending on what it has. One of the trivial cases is if xt is, let's say, x0 cosine of omega t plus theta. Now you understand why we introduced that deterministic random process? This is an example of a deterministic random process, alright, where theta is the random variable, and we assume that theta is uniformly distributed. What is the range of theta? 0 to 2 pi. We assume that p theta is uniformly distributed over the range 0 to 2 pi, and the value naturally shall be 1 over 2 pi. We assume that it is so. Now, if I calculate, I don't have anything else. It's just a random variable, x0 cosine omega t plus theta. It is periodic. Alright. Now, if I calculate the autocorrelation function of this random process, that is, Rx tau would be E of x0 squared cosine of omega t plus theta multiplied by cosine of omega t plus omega tau plus theta. Why is it so? Why theta again? Theta is a random variable.
It's not a function of time.
Because it's autocorrelation. We are taking x of t1 and x of t2 from the same process. Alright. Theta for another member of the family shall be different. But as far as, suppose for another member of the family it is theta 1. Then for both x1 and x2 it is theta 1. Now, it is a matter of trigonometry now to expand this into a sum of two cosines. Okay, one of them will be cosine of omega t
plus theta plus omega t.
Yeah, one of them would be 2 omega t plus omega tau plus 2 theta, right? Yeah, cosine A cosine B is cosine A plus B. Okay, and the other would be cosine omega tau. Theta and theta will cancel, and you can show that this is simply equal to, I leave that demonstration to you. It is simply cosine omega tau. That is, Rx tau also has a periodic component with the same frequency omega. And you can also show now, it is also a matter of algebra now, that if x of t was x0 cosine of omega t plus theta plus some other component which is non-periodic, let's say again n of t, this is not periodic, periodic component is this, then you can show that Rx of tau contains x0 squared by 2 cosine omega tau plus Rn tau, which is non-periodic. So, what we learned today is that the autocorrelation function is a faithful reflection of the nature of the random process. If the random process is a DC component, autocorrelation function also has a DC component, and vice versa. If the autocorrelation function has a DC component, then the random process must have a DC component. Similarly, if the autocorrelation function is a periodic component, then the random process must also have a periodic component. And this is where we shall start next time.